Thank you. In a recent discussion on the Foren's Internet discussion list, there was a comment that there were sort of two kinds of forensic science. There was the scientific kind of forensic science, by which they meant DNA, of course, and there was the non-scientific kind of forensic science, by which they meant most everything else. And the DNA is the new model for forensic science. In a recent article in Science magazine, the statement was made that traditional forensic scientists seek to link crime scene evidence to a single person or object by leaning on the assumption of discernible uniqueness. The fact that the authors of that editorial, I guess you'd call it, in Science magazine believe that discernible uniqueness is as they call it, a central assumption of forensic science may indicate that we have not done a very effective job of communicating what we do to other members of the scientific community, especially our critics. Or maybe it's an indication that we don't understand ourselves what we really do. I think the first step in convincing others that we have something of value to add to the judicial system is to develop the full value of what we do. There must be a better way to express our conclusion than it could have come from. If nothing else, an experienced trace evidence analyst should have some sense of how common it is to find matching fibers on two items that have not been in contact. The value of experience in this should not be underestimated or ignored, again, as Ken Wiggins' demonstration pointed out. But in order to conduct a scientific investigation, which is what we should be doing, we must understand a few principles. These principles may seem obvious and irrefutable, but they're nevertheless important to explicitly state. Then we must consider how these basic principles that we use, how to take advantage of these principles to arrive at answers that we hope to obtain, and then put these principles and processes together with the limitations imposed by the nature of the job, and that all defines the paradigm under which forensic science is conducted. Well, it's going the wrong way. Principles are things that we cannot prove, but they're applicable to all areas of forensic science. All areas have certain principles. One of the first principles in criminalistics was stated by Paul Kirk in 1953 edition of Crime Investigation: no two objects in nature are identical. We can't prove that proposition because we can't compare all two objects in nature, but we believe it to be true, and I think in one way or another that statement is certainly true. We are continually searching for techniques to determine the uniqueness of objects, but it is not the uniqueness that is the problem we're trying to solve. Rather, it is a determination of properties that are shared by two objects, which suggests that they may have either a common origin, were produced by the same operation, or that one object was produced by the other. The principle of individuality describes why it is possible to establish links between evidence and exemplar items. Principle of divisible matter has been introduced by Keith Inman and Nora Rudin in a recent book, and I've sort of modified their statement of that principle to the statement here on the screen that says matter divides into smaller components when sufficient force is applied. It's intuitively obvious, but the principle of divisible matter has some corollaries that help us understand physical evidence. The first is that the process of division may produce pieces that are unique to the two pieces. It may produce two different pieces. Second, when an object is separated into pieces, some features of the one piece will be retained by the separated piece. And third, the passage of time may affect the two pieces differently. I think these are all corollaries of a principle that we need to keep in mind of divisible matter. The final principle is one that we're all familiar with, is the principle of transfer, Locard's principle, which states that basically that when two objects come into contact, matter will be transferred from one object to the other and from the other to the one. Are there corollaries to that principle? I think there are. When contact occurs between two objects, the transfer may be in either or both directions. The rate and quantity of transfer depends on the properties of the material involved in the materials in contact, the forces involved in the contact, and the time of such contact. And the persistence of transferred material depends on the properties of the transferred matter, the properties of the recipient object, and the post-transfer actions affecting the recipient and transferred objects. The principle of transfer and its corollaries describes how physical evidence becomes separated in space. Obviously, that's important. These three principles, at least, and there may be others. I'm not saying that these are the only three principles that we need to keep in mind, but I think these are three, are utilized in a series of processes that can be defined as unit operations. A unit operation can be defined as a structure of logic used for synthesizing and analyzing processing schemes in the chemical and allied industries, in which the basic underlying concept is that all processing schemes can be composed from and decomposed into a series of individual or unit steps. So if you're conducting a scientific investigation based on the principles that I've just enumerated, what are the unit operations involved? I think the first unit operation is recognition. We need to understand and locate the matter, that is the physical evidence that will inform us about the circumstances of an event. That's the first step in the scientific investigation that we are conducting. The process of recognition is not simply one of perceiving or seeing it, it also implies an understanding of it. How can this matter inform us about its circumstances? How did it come to be lying on the floor of the scene? And what matter is there that might inform us about matters that we're concerned with in the investigation? The second unit operation is preservation. Preservation is the operation of conserving the properties of physical evidence that are relevant to the scientific investigation. This may seem like a simple operation. Put it up, put it in an appropriate container so that it will not get ruined, so the lab can do whatever examination I ask for, or they can do with this evidence. But what about the unusual, the unexpected, or the unobserved? What about properties of evidence that are not conserved with changes in that object's environment? Preservation begins with the moment evidence is first recognized. The next operation is identification. Identification is no more or less than giving something a name. There are many ways of naming things. A fiber, a common name, a human hair, a technical name, quartz, a chemical name, sodium carbonate, a trade name, nylon, or simply a descriptive name, a red birefringent particle. Those are simple steps that we all are pretty familiar with. The fourth unit operation is individualization, the process of determining that two things have a common origin. Just as identification is a process without any necessary endpoint, so is individualization a process without any necessary endpoint. The final unit operation in criminalistics is reconstruction. In general, criminalists are routinely concerned with reconstruction, the persistence and transfer of trace evidence material, interpretation of blood spatter patterns, determination of bullet trajectories, fracture or damaged objects are all matters of reconstruction that criminalists deal with. But I would also add that reconstruction involves the determination of how evidence came to be. So you may only be reconstructing how a fiber came to be on the sole of a pair of shoes, for example, as a paper earlier today illustrated. So that is as much a reconstruction as a determination of a bullet trajectory or interpretation of a blood spatter pattern or any other investigation that allows the physical evidence to inform us about what happened in the event that's being investigated. And all of those unit operations are necessary in the criminalistics operation. I've been especially struck by the papers I've heard here this week about the importance of the reconstruction, not of the incident, but of the nature of the physical evidence. And there is a whole lot of information that's available in various technical and scientific publications about how that reconstruction can be done in a very formal way. And if we understand how it's done in a formal way, then I think people will give the work we do some credibility, or some more credibility. Forensic science is one of the several applied science which have the responsibility of reaching a conclusion and applying that conclusion to the resolution of some matter. This matter may be the diagnosis of an illness by a physician, the resolution of a manufacturing problem in a production facility, the reconstruction of an archaeological site, or the reconstruction of some recent event during which a crime may have been committed. Each of these disciplines have their own set of problems. Living patients make certain diagnostic procedures difficult, for example, autopsies. Artifacts buried underground for hundreds and thousands of years are not properly preserved. Manufacturing widgets, which somehow go awry, can just be thrown away or recalled, as we've seen recently. Forensic scientists are faced with a task that is not common necessarily to any of those professions, and it's not common to the general operation of science. We investigate a specific incident rather than a material. We can do all the analysis we care to of a material and generate reams of precise and analytical and accurate data, but if that work does not lead us to a greater understanding of the incident, it is of no value. We also have to come up with a conclusion that has essentially permanent consequences, at least to a few people. Whether or not, what is or is not evidence is not always immediately apparent. Issues may not be well defined or even known at the time the collection of evidence is possible. Sometimes a decision about the event has to be made on factors other than what best serves the scientific investigation. There may be conflicting evidence, such as eyewitnesses or motives, which will be considered when the ultimate decision is being made. Forensic science investigation has problems which are no more or less, they're just different from problems in other applied science endeavors. Even though the problems may be somewhat different in various applied science disciplines, the problems can be generally recognized by two types of errors: technical errors and cognitive errors. Technical errors are such things as sample mix-up, laboratory contamination, failure to run controls or calibrations, unavoidable analytical errors, analytes are below limits of detection, there may be unknown interferences that give misleading results, or there just may have simply been a human error in reading the data. Some of these mistakes can lead to disastrous results, some are relatively benign, but many, if not most, can be detected by quality assurance programs. Cognitive errors are errors of a different sort. These are errors in thinking, in not understanding the question that is being asked, not considering alternative explanations for observations or test results, not thoroughly investigating the significance of laboratory findings, or not understanding the power or limitations of a particular techniques. Techniques to recognize and address these errors are the subject of philosophers of science. Charles Peirce, a 19th century American philosopher, suggests that the application of logic can help resolve these problems. Karl Popper, a 20th century philosopher of science, proposes that rigorous experiment can eliminate alternative hypothesis until, in the words of Sherlock Holmes, whatever remains must be true. Thomas Kuhn advises that explanations that make sense, that are pragmatic, are the best explanations. Statisticians have developed statistical approaches for the evaluation of data and subsequent decision making. In proceeding towards the resolution of a scientific investigation, it is of great help to understand the nature of the various cognitive errors that can be made in the process. There are many such errors, but a few examples will suffice for the purposes of this presentation. One common error is the fallacy of efficiency. It's an error resulting from over-reliance on some efficiently and easily obtainable data. Following protocols is certainly inefficient, as efficient as the protocol allows, but it also may be limiting. Protocols are by their very nature assigned to be applicable to the typical case. If the protocol is followed in the atypical case, the results may be efficiently obtained, but may be misleading or irrelevant. Kuhn describes this error when discussing the process of proceeding under any specific paradigm. Fact-finding under any specific paradigm, a term which Kuhn uses in much the same way as a hypothesis, results in finding facts that are amenable to casual observation or experiment, or in some cases more esoteric data obtained from crafts. Forensic laboratories have many craftsmen who generate esoteric data. Relying on such data may prevent us from discovering explanations outside the operative paradigm. Another fallacy is the genetic fallacy, which leads to the error of determining the validity of an idea based on its origin. We commit the genetic fallacy when we reject an idea based on the technique used to arrive at the idea, or accept uncritically an idea based on its origin. Another fallacy is the fallacy of expectation. When scientists conduct an investigation, they do so with a common understanding of the assumptions and methods of operation of their science. Kuhn describes this as their paradigm. As a consequence, they expect to receive particular results. So when scientists conduct an experiment, they design, conduct, and interpret the experiment within the context of the paradigm under which they work. Kuhn describes the fallacy of expectation with the following example. Solving a jigsaw puzzle is a problem with a commonly understood paradigm that involves fitting the pieces together by a certain process which results in a complete image of some type with no open spaces and without the use of special tools. A puzzle solver who randomly arranges puzzle pieces on a blank piece of paper may create a very artistically pleasing solution to the puzzle, but it's not one that jigsaw puzzle solvers would think was appropriate. On the other hand, jigsaw puzzle solvers would consider themselves misled if they were asked to solve a jigsaw puzzle composed of pieces randomly selected from 2 or more jigsaw puzzles. That's not part of their paradigm. The conduct of a scientific investigation involves a formulation of a hypothesis. This is not a trivial proposition, as illustrated by an example from Charles Peirce. There are 2 logical processes that we're all familiar with. The first is the deduction. We have a jar of blue marbles. We select the marble from the jar. We hypothesize that the marble will be blue. So we make an observation, it is a blue marble, the deduction is proven, but we haven't learned anything from that operation. Another logical construction is the induction. We have a marble from this jar. The marble is blue. Our hypothesis is the jar contains blue marbles. We ask, what color marbles does this jar contain? We look into the jar to confirm our hypothesis. Maybe, though, we have selected the only blue marble from the jar, and which now contains only red marbles. What can we conclude? The third logical formulation introduced by Peirce, he calls the abduction. The abduction is the following process. We have a jar with blue marbles. This is a blue marble. Our hypothesis is the marble came from this jar. Very different question than the induction. Forensic scientists should recognize that this is the problem which we're faced with. This is the problem of individualization. This is the problem that defines the hypothesis and the experiment that we need to conduct in order to prove the meaningful hypothesis in the case that we are investigating. The determination of the properties of 2 objects that establish they have a common origin is simply, or they could have a common origin, is a technical operation that precedes a consideration of the question of concern. Kuhn describes this as the mopping up operation. Given that the jar has blue marbles in it, The real question to be addressed in the forensic science investigation is, was this evidence produced as a result of the event under consideration, or what does this evidence tell us about the event that we are investigating? If we look at this, well, I'm going to skip past this for a second. We have to, in designing these experiments, we have to look past the normal inductive problem, because it really doesn't get us where we want to do, and we have to avoid some thinking difficulties that come up when you're designing experiments and testing hypotheses. You have to think outside the box. You can't just think straight ahead from where you think you're going. You have to think outside the box. We have to avoid the Occam's razor problem. We like to use Occam's dicta that the simplest explanation is the best. It may not always be the best, and we need to think of the more complex hypothesis to test. We also have to be aware of what's been called the modal fallacy, confusion of terms. We confuse the terms frequently of could be and is, so we have to be aware of those alternatives. We generally rely on the two principles of divisible matter and exchange to explain how evidence came to be present. But neither of these principles relies on the assumption of the presence of the material that was a consequence of any specific act. These principles simply state that when certain phenomena occur, certain results will be present and can be observed, and either the transfer or alteration of some physical object. So we must consider and devise experimental ways to reproduce and measure the consequences of actions and interactions that could have produced the evidence. In other words, we must test various reconstructions to see if they produce the evidence that was found, and then we must consider the certainty with which the evidence produced by those actions would have been found. We cannot generally go back and look for that evidence after we've done the experiment. This places a rather daunting burden on the initial portion of the investigation, that is the crime scene, because we can't do an experiment that would produce evidence that we can then go back and look for. We have to already have that evidence, or the chances are we won't be able to collect it. Okay, the crime scene is a puzzle. The pieces of the puzzle are physical objects at the crime scene, and we can't force that into the jigsaw paradigm, because the jigsaw paradigm doesn't work, because we do have extra pieces, we do have missing spaces, and so it's very difficult to be sure that we've solved the puzzle correctly, because it's not as simple as a jigsaw puzzle. We need to develop the paradigm that we use in a way that we can explain it to others, and to use methods of validating that are valid within the paradigm that we work, and not fall into the trap of relying on others to define the paradigm, whether they be the DNA analysts or people that say that we use discernible differences as our paradigm. We must invent our own paradigms and then develop ways to show that that's a valid way of conducting the scientific investigations that we're expected to conduct when we're working on a crime scene. Thank you.